Hello, calculus type people. Hope you're having a fantastic day today. Today we're going to be talking about cross sections other than circles. Up until now we've been talking about discs and washers, which all have the same basic shape. They're all circles, right? So today we're going to be talking about something. Well, what if you don't want to use a circle? What if you want to use a square or a rectangle or a triangle or any other form of area? And there's actually a project that goes along with this section, which hopefully we'll get to after the AP exam. So that'll all be fun. Anyway, example number 1. It says, let the base of a solid be in the first quadrant plane region bounded by y equals 1 minus x squared over 4. Now the key to this are the first few words, the base of a solid. It's bounded by the x-axis, the y-axis in this graph. So first, let's go ahead and draw it. The x-axis, the y-axis, and this graph, this is a negative parabola, very wide because it's divided by 4, shifted up 1. So it's going to look like this. And it's the x-axis, the y-axis, and this parabola. So I'm looking at just this part right here. Between the x-axis, the y-axis, and that guy. Suppose the cross sections perpendicular to the x-axis are squares. Perpendicular to the x-axis means that we are going to be using this. I'm looking at delta x, which means I need a dx. Alright, and I'm going to give you a few little tips here, and you're supposing that my cross sections are squares. What this means, and let me kind of get a little thing to show you here. I have a square, little piece of paper, right? What they're saying is that you're not revolving this, but you are taking a cross section. So imagine that square coming up off the page and being as wide as your function. Kind of like that right there. It may help if I need to prepare a little bit better. May help if I do this. Okay, so we have a square. Now if I line this square up with where I'm perpendicular to my x-axis, pretend this is actually a flat square, this is basically what they're looking at. It's coming up off of my graph, and how wide that square is going to be determined on how big my graph is. So obviously over here we're going to have much smaller squares. Right here, because the square is the same on all 4 sides, I'm going to have bigger squares. Right? So here's how this is going to work. The very first thing I need to do, I'm going to give you a list of steps here. Step number 1 is to find the correct area formula. Find the correct area formula. For squares, it's s squared, but we'll get to that in a second. Actually, let's get to it now. Why not? Number 1. Step number 1. Area of a square is s squared, the side squared, right? 2. You need to find the parts needed for the area formula. Find parts needed for area formula. For a square, it's just I need to figure out what the length of the side is, right? So my side is S, which my side of this square right here, here's my square, the side of that square is going to be however long my function is. So up here I'll have a bigger square, down here I'll have a smaller square. So it's just going to be my function. 1 minus x squared over 4. And then 3, this is the big one, the formula. Volume for a cross section, CS, is the integral of area, the formula for area. So it's a pretty simple idea here. VCS is the integral of 1 minus x squared over 4 squared. This is your side. Area is side squared, so it's the integral of that squared. And I'm integrating with respect to x from over here. So I need my values for my x's. How far over does this go? Where does this intersect the x-axis? So set it to 0. 1 minus x squared over 4. And subtract 1, divide by -1, multiply by 4, you get x squared equals 4. So x is positive -2. So this is 0, this is 2. Integral from 0 to 2. So it's a pretty basic process. Find the formula for area. Your side is the length of this your function here from the x-axis up, and then volume is the integral of your area, s squared. And this is going to be, I've already done this ahead of time. I'm going to go ahead and start putting U for units on there. 1.067 units cubed. All right, so in the interest of time, let's see if we can make this go a little bit quicker here. Down here, back up just a hair. The base of a solid is the region bounded between the arc of, that should be arc of y equals sine x and the x-axis. Each cross-section perpendicular to the x-axis is an equilateral triangle. Ooh, fun. Equilateral triangle sitting on its base. The base is this guy. So I shouldn't have to spend too much time on this. You know what the sine wave looks like. It starts at 0, 0, goes up and comes back down at pi. Right? And here's 1, and it hits 1 at pi over 2, right? So step number 1, find the area, and in this case it's area of a triangle. Right? Find the area of a triangle, equilateral triangle. Now an equilateral triangle, it does have a certain area. It's an interesting one anyways. You could do 1/2 base times height, but you'd have to find the relationship between your height. I'm not going to do that for right now. There's actually a special formula for an equilateral triangle I want to give you. It's a shorter way. Square root of 3/4 s squared. It takes your square and it cuts off the extra stuff you're not using, so it's just square root of 3/4 x squared. And that's for equilateral triangles. Number 2. Again, I will do one with a base and a height a little bit later, but for right now I just want to keep this a little bit more simple. Number 2 is to find the parts needed. So I need the side, which is my sine x. And if you can imagine it, let me see if I can make this work. Okay, here is my equilateral triangle, right? And it's sitting right here. Do it this way. It's sitting here, and it's coming up straight out at a 90-degree angle, building up like this. And there's tons and tons and tons of these things in here, right? Infinite numbers in here. So what you're looking at is step 3. Oh wow, volume. CS is the integral, square root of 3/4. Sine x is your s value squared. dx, it's perpendicular to the x-axis, means that it's going to be coming up here. So this is your delta x, which means you're using dx. Here's the area you're trying to find. And then limits of integration from 0 to pi. and that's going to give you, roughly, being in radians, make sure you're in radians here, 0.680 units cubed. Again, this is for equilateral triangles. I will give you something on the other side for rectangles, which is a little bit different. But just remember that equilateral triangles, this is a special formula for equilateral triangles. Square root of 3 over 4 s squared. What this does is it takes away having to figure out what your height would be. It just takes that out of there and sets it up as a ratio. So let's see what we got. Example, where was that? Number 3, right there. Base of a region in the xy plane bounded by this guy, and x equals 0. So first let's draw it. X equals 4 minus y squared. That's going to be x minus 4 equals negative y squared. So positive negative square root of 4 minus x. So it's a negative x value moved right 4. 1, 2, 3, 4. Up like this. Down like this. X equals 0, so it's all of this. Okay. And it says find the volume if the cross sections are perpendicular to the x-axis. So again, I'm looking at delta x, which means I need dx. Few pieces of information that are probably going to be useful for a couple of things here. Number one, since I need dx, I'm going to need it in this format. I'm going to need it to be solved for y here so I can get it with x's in here. So that's going to be useful. So let's see what we get. A says semicircles with diameters on the base. So it's a semicircle, right? It's coming up off the page going blue. It's a semicircle. So number one, area of a semicircle is 1/2 pi r squared. It's a circle cut in half. Your radius. Now this one, let me see how I want to do this one here. Well, the 1/2 will take care of itself. Diameters on its base. 4 minus x. Oh, duh. Okay. Square root of 4 minus x. Now the radius is only half of this, so I'm just going to use the positive half from here to here. So just the plus square root of 4 minus x. So volume of your cross section is going to be the integral 1/2 pi r squared dx. And my limits of integration using my x values are from 0 to 4. That's the lowest x value to the highest x value. And that is 12.566. So again, the tricky part here was the radius. I got tripped up for a little bit there, but the tricky part's the radius. I only want, if my diameter goes across the whole thing and it's popping up this way, it's going out at you, right? If it's popping up, then the radius is just going to be the positive portion. And then B is rectangles. Now here we go, rectangles with height half of the base. So first, the formula for area of a rectangle is base times height. So now we need to identify the parts that we need for this. Well, the base is going to be all of this, right? So it's going to be the distance from the top to the bottom. Unfortunately, I can't do a plus or a minus. So what I'm going to do is call it the diameter of this thing. Now the radius of this thing was here to here, so the diameter is doubled. So I'm going to call my base 2 of the square root of 4 minus x, because this is kind of like saying your diameter, right? This is kind of like your diameter. And then my height is going to be half of that. It's 1/2 of my base, so it's going to be 1/2 of this, which is the square root of 4 minus x. 1/2 of that. So volume then, this thing kind of comes together, is going to be the integral, again from 0 to 4 because we're integrating with respect to x. And then plug this in here, it's base times height, so 2 square root of 4 minus x times the square root of 4 minus x, base times height, dx. And it actually comes out to a perfect 16. All right, one more here. Find the volume of a solid whose base is bounded by the graphs of y equals x cubed, y equals 0, and y equals 1, x equals 1 rather. Let's draw it first. Y equals 0, x equals 1, and x cubed, which does something like this. Then it pops down over there. Remember that guy? And they come together here at the point 1 comma 1. Obviously 1 cubed is 1. It says cross sections are perpendicular to the y-axis now. Oh, good. So here we go. We're using delta y, which means dy. So number 1. And they're equilateral triangles. Remember that 3/4 s squared? Square root of 3/4 s squared? A equals the square root of 3 over 4 s squared. Equilateral triangles. Section 2. Figure out what one of the sides is. Okay, now this one's going to be a little bit different because the side is out here. It's away from our axis. This is one of the first ones we've done where it's actually away from the axis. Notice I'm missing this little piece right here, so I have to account for that. So I'm just going to say it's 1 minus whatever this is. My side is going to be 1 minus the cube root of y, because I need to get rid of this little empty space. Remember that all I'm doing is building a triangle here, 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 lots of little triangles. So number 3, volume of a cross section is the integral. We're using y values here, so from 0 to 1 of 3, square root of 3 for 4 s squared 1 minus, let's go ahead and do y to the 1/3 squared dy. Just so you're able to type that into the calculator a little bit easier. All right. So to recap everything here, for volume, we've got three volume formulas. We have our rotations, which is going to be your disk and your washer method. Disk method is pi the integral of r squared. Washer is going to be pi the integral of r squared minus little r squared. And then you've got your cross sections. BCS is the integral of area. So it's not that difficult of a concept. I want to bring in some manipulatives hopefully tomorrow to kind of shore up the process or the idea, the concept here. Have a good one.